Hello and welcome to week 8, where the unifying theme for our discussions is going to be randomization, which turns out to be a really powerful strategy for the design of efficient and very often elegant and cool algorithms, which turn out to be fairly popular in practice because of their ease of implementation. They often tend to be tricky to analyze, and we'll see a few interesting examples this week. We're going to actually start off with randomized quicksort. So this is not even about a hard problem, but it'll be a good illustration of principles that keep coming up. So that's where we're going to begin. I should make a couple of disclaimers up front. First of all, we are not going to be discussing the philosophy of randomness and issues of, how do we source random bits and things like that. That's well beyond the scope of what we're up to. We are just going to assume that we do have access to random bits and that we can have our computers reliably flip coins for us. If the issue of how they manage to do this is of interest to you, you're welcome to check out some of the references in the course materials where you can find out more. And the other thing is to alert you that we're going to be mostly talking about algorithms that are randomized as opposed to a closely related theme, which is the probabilistic analysis of algorithms, which may be deterministic. So to run a probabilistic analysis for an algorithm usually means looking at input distributions and trying to analyze the behavior of the algorithm in question with respect to a specific input distribution. You say, well, suppose I knew that my inputs are being drawn from a particular distribution, then what can I say about the expected running time of my algorithm? And that's a perfectly valid set of questions to ask. It's just that that's not going to be our focus this time. We are going to be dealing with a situation where the randomization is in the implementation of the algorithm itself. So every time you run the algorithm, it's potentially a different story, and you want to analyze the behavior of the algorithm in aggregate. So we're not going to be doing analysis of input distributions. We're going to assume that all inputs are equally likely, but we are going to actually look at the behavior of the randomness that's inherent to the algorithm itself. Broadly speaking, there are two kinds of randomized algorithms. They often go by the terms Las Vegas and Monte Carlo. So what's the distinction here? Well, when you're looking at a Las Vegas algorithm, then you're always guaranteed to have the right output. So the algorithm never makes a mistake. However, depending on how the algorithm pans out, it could take different amounts of time on different runs. So you could have some runs that just turn out to be really expensive if you're unlucky, and some that turn out to be cheap if you are lucky. And the analysis of such an algorithm often involves in coming up with bounds on the expected running time of the algorithm. So that's Las Vegas. Monte Carlo algorithms, you actually allow yourself a little bit of error. So you might actually produce the wrong output, but hopefully on only a small fraction of runs. So here what you're interested in doing typically is bounding the error probability. The algorithm usually has a fixed run, and it's the time can be estimated in sort of a typical worst case kind of analysis exercise, but what you are unsure about is whether the output was okay or not. So you try to bound the error probability, and often you would use techniques like boosting, which involves running the algorithm multiple times to bring the error probability further down. So let's summarize what we just said. Between Las Vegas and Monte Carlo, we are simply making different choices on what we want to gamble on. There are two elements of interest here. One is the correctness, and the other is the running time. So the gambling happens for Las Vegas algorithms on the running time, because that's what you're willing to sort of experiment with and compromise on. And with Monte Carlo, the running time is fixed, but you gamble on the correctness. This is a quick example borrowed from Wikipedia to illustrate the difference. So suppose you have an array which is half zeros and half ones. Now the goal here would be to find an index which has a value 1. Now the Las Vegas approach to this problem could be simply to say that let's ping random indices until we find a 1. And given that we are promised that there are 1s in the array, we always terminate correctly, right? What we don't know is how lucky or unlucky are we going to get with our random choices. It's possible, although extremely unlikely, that we have to ping n by 2 plus 1 entries before we find the 1. On the other hand, a Monte Carlo approach to this would be to, well, keep pinging till you find a 1, but have a cutoff of, let's say, 300 or something. So you could say this is a constant independent of n. You could also come up with a threshold that's a function of n. Let's say you say that we are going to ping log n many entries, a square root n many entries, until we find a 1. Well, of course, we stop if we find a 1 because we are done. But if we go through all the iterations and we haven't found a 1 yet, then we just report failure. And that would, of course, be an error given the promise that we know that there are 1s in the array. So in some sense, you could think of that as a wrong output situation. But you could ask yourself, well, what's the probability that you end up in the bad situation? And of course, the analysis will be different depending on what the threshold you choose is. But the point is that there is an error probability, which you hope is small. And you can imagine that it's also tied to, like we just said, the threshold. So the more iterations you're willing to go through, the smaller your error probability is going to be. But that's basically the distinction between the Las Vegas style and the Monte Carlo style. With the Las Vegas algorithm, what you would be analyzing is the expected running time. So sometimes you might just be so lucky that your first hit is actually a hit. But if you're super unlucky, then you're going to have several misses to endure before you actually find your hit. And the question is, well, what happens on average? So you want to analyze the expected running time of the Las Vegas variant. So that's it's an interesting exercise, I think, that I'm going to leave you with in the context of these definitions. And now with that said, let's go ahead and talk about randomized quicksort, which is our first example, as promised, of how randomization helps out. So recall that the problem we are concerned with is sorting. So let's say that our input is an array of n distinct integers. Now, the distinctness assumption is not particularly crucial. You can get rid of it, but I'm just making it to keep our discussion simple. But everything really carries over to the situation when you do have duplicates in the array. Now, what we expected to do is to sort the given array. And the way we do this in quicksort is to pick a pivot, which is one of the elements of the array. So let's say that for convenience, I'm just going to default to the first element of the input array, which I'm going to denote by A. And this pivot determines what we are going to do next, which is essentially to recurse on two subarrays, which we are going to now build. So the subarray A1 is going to consist of all elements in A that are less than A0, and the subarray A2 is going to be all elements in A that are greater than A0. So you get these two subarrays, and we are going to recursively run quicksort on both of them. And when we do that, we are going to get back sorted versions of both the subarrays. And at this point, we are in business because we can simply return the output of quicksort on A1, followed by the element A0, followed by the output of quicksort on the array A2. Notice, by the way, that when your array has just one element in it, then quicksort is going to return that element without having to make any further recursive calls. This is because A1 and A2 are empty, and also when your array has just one element, there's really nothing to be done. So that would be an informal description of what Quicksort does. And of course, if you actually cared about an implementation, you'd have to worry about several details. But allow me to point out how it's fairly clear, even from this description, that Quicksort does the right thing. The correctness, I would say, is pretty transparent. Because this is a recursive algorithm, you would want to argue correctness using induction. And of course, the base case is nothing going on. The algorithm is trivially correct. And in general, notice that what you return is the output of Quicksort on the subarray A1, followed by the pivot element, which is A0, followed by the output of Quicksort on the subarray A2. Now, notice that, well, the induction hypothesis is going to give us the guarantee that these two subarrays here are fully sorted, and that's just because that's Quicksort acting on a strictly smaller input, so we're going to assume that it does the right thing. And just by construction, we know that A0 is larger than everything in A1 and is smaller than everything in A2. And by the transitivity of those inequalities, we also know that everything in A1 is smaller than everything in A2. So really the whole thing works out. All the relative orders are correct and your final input is indeed sorted. Now, in terms of implementation, that's also fairly clean. So usually Quicksort is implemented in place, and to do that, we're going to write Quicksort as a function that takes an array as input and also a pair of indices P and Q, which indicate what's the subarray that's currently in focus, what's the subarray that we want to sort now. And this is to say that we want to sort everything that sits between the indices P and Q, PQ inclusive. So that's going to be our focus. So Quicksort of the array A with indices PQ is designed to ensure that the subarray consisting of all elements between the indices P and Q inclusive is sorted once this function has done its job. So notice that to begin with, when you want to sort the whole array, the lower index is going to simply be 0, and this upper index would be n-1. Of course, this is assuming that the arrays are indexed starting from 0, and this would simply mean that we want to sort the whole subarray. And of course, as we go along, we are going to continue to break this up into smaller and smaller subproblems, as we will see in a moment. But in general, when you're trying to sort the subarray between P and Q, we're going to begin by picking a fixed pivot. As we said earlier, let's commit to the first element in the subarray being the pivot. And what we are going to do is basically run a sort of a partition procedure, which will simply ensure that the subarray is reorganized so that wherever the pivot is, everything that precedes it is smaller than it, and everything that succeeds it is larger than it, at least within this subarray. And you can achieve this by simply doing one pass over the subarray and swapping things appropriately. So one way to visualize this is that you have some sort of a barrier which maintains the invariant that everything to the left of the barrier is going to be smaller than the pivot, and everything to the right of it is going to be larger than the pivot. And you sort of have a running index which goes over the whole subarray, and every time this running index encounters something that's smaller than the pivot, then you essentially have it swap with whatever is next to the barrier, and then you upgrade the location of the barrier to move one unit further. So if you just keep doing this as you go from left to right, you'll be in a situation where the first segment is going to be, the first segment up to the barrier is going to consist only of elements smaller than the pivot, and everything after is going to be larger than it. And at the very end, what you can do is take the first element that comes before the barrier, the final location of the barrier, and swap that out with the pivot element. So that brings the pivot element right in the middle, and it gives you two nice subarrays which have the properties that we want out of A1 and A2, and you can then sort of recurse. So assuming that the pivot landed up at, let's say, an index that I'm going to call R. So what you're going to do from here is basically run Quicksort on the subarrays p r minus 1 and r plus 1 up to q. May have to be a little bit careful about edge cases and such, but that's essentially what you want to do here, and Quicksort will delve further into these subarrays and make sure that they're sorted so that by the time you come back from these functions, so by the time you're here, the entire subarray is sorted. So you should probably be a little bit careful about the edge cases here. In an actual implementation, you'll probably have some extra sanity checks thrown in. For instance, you might want to ensure that P is actually strictly smaller than Q, otherwise this doesn't make sense for the most part, and so on. But this would be a very typical implementation of Quicksort. I haven't written out how the one-pass partition algorithm works, but hopefully that's straightforward enough that you can write it out if you would really like to. And that's basically it. Once you've recovered from these two function calls here, notice that you will indeed be in a situation where the entire subarray between P and Q inclusive is sorted, and that's why if you look at the call right at the top, once you are done, you're really done. Everything is sorted. All right, so we have discussed the mechanics of Quicksort, and we've also analyzed it for correctness. So now let's talk a little bit about the running time. So as we have presented Quicksort here, it's a recursive algorithm, so it's most common to think of the running time also being expressed as a recurrence. But before we get into writing it out, let's really think about what's going on here, right? So when we begin, we have an array of length n as input. That's what gets fed into the Quicksort algorithm at the top. And based on the choice of pivot, what's going to happen is that we create two smaller instances, and I will call them A1 and A2, although in the actual implementation, it's still going to be the entire array A with pointers to extract A1 and A2 out of it. But for now, bear with me, I'm just going to write it this way. And the question that's really worth thinking about here is, how does the split affect the running time of the algorithm? So how do the sizes of A1 and A2 drive our discussion about the running time of the algorithm? So for example, in particular, would it be nice for us if A1 and A2 were roughly the same size, or would it be good if one of the subarrays carried the bulk of the instance forward and the other one was almost empty? So for instance, would you be happier if A1 was empty and A2 had n-1 elements in it, or would you be happier if A1 and A2 both had, let's say, n/2 elements in it? Both of those scenarios, assuming that that's how they continue to play out for the rest of the choices that are being made, that's a huge oversimplification, but that those are scenarios that could happen. So let's just focus on these two extremes. One is that at every step, the pivot happens to be such that it always splits the array into roughly two equal parts. I'm saying roughly because you may not always have an even number of elements to work with. So by roughly, I just mean that it's n/2 up to floor ceiling off by 1 and so on. So you're in that situation, versus the other situation is that your choice of pivot is such that it always completely eliminates one of the subcases, and it leaves the entire remaining subarray in the hands of just one of the recursion branches. So A1 is empty and A2 has n-1 elements, and this pattern keeps repeating with every subsequent choice of the pivot as well. Which of these recursion patterns would you prefer? I would really suggest taking pen and paper, especially if you haven't done this before, and working through both of these scenarios and trying to get a sort of a guess estimate of the running time in both cases. So come back when you have had a chance to do that. All right, so let's first think about the case when you have a roughly even split on the array at every step. The shape of this recurrence tree might remind you of another sorting algorithm that you may have seen before, which is merge sort. That's also a classic divide and conquer approach to sorting. And in merge sort also, you always end up partitioning the array into two equal parts at every step, and then you sort them recursively and then you put them back. One contrast between merge sort and quicksort is where the work happens, when we are talking about the work happening at the node. So at every point in this recursion tree in merge sort, the work happens after the recursive calls are done, because that's when you run the merge procedure to put back these two sorted arrays together, and that takes you linear time. Whereas in quicksort, all the work really happens when you're trying to determine this initial split. So the work that happens in this call to the partition function. And that's again linear time. You have to, like we just discussed, really just do one pass to figure out what the partition looks like. But you do have a linear time expense in just figuring out what the split looks like. So that happens up front. But what happens after the recursive calls are done is basically constant time, because you just need to, you really just need to return the array when you're doing it in place, because everything is done for you in the recursive calls themselves. So basically putting everything back together comes for free in quicksort, whereas determining the split takes linear time. In contrast, in merge sort, the split itself is trivial, because you just split it right in the middle, and you immediately make these recursive calls. So the work that happens really happens at the time of merging the outputs. So that's an interesting contrast. But now the other point of contrast that I'll draw your attention to is the fact that the recursion tree for merge sort is always going to look the same irrespective of what the input is. It's really a fixed structure, and it's going to look like this. At the top you have an input of size n, and you're going to split that in the middle, and so you get two instances of size roughly n by 2 each. And well, I mean, I realize I'm not being very precise here, so n may not be an even number. So this is going to be floor n by 2 on the one hand and ceil n by 2 on the other. But between us, I'm going to gloss over that level of detail, because what I really want to emphasize is sort of the big picture here. At the next layer, you're going to get 4 instances of size roughly n by 4 each. And if you take this all the way to the end, then you'll see that you have a tree whose depth of recursion is going to basically taper out at log n levels. And since you're doing a linear amount of work at every node, you can see that the total amount of work that's being done at every layer is essentially n. So your overall running time amounts to n log n. So that's what the merge sort recurrence looks like. And if you don't remember how merge sort works, then don't worry about it so much. You could just stare at this tree and realize that this is how quicksort could go if your choices of pivots happen to be really lucky, or maybe if you always pick out the median element as the pivot at every step. But then you have to be careful, because you pay an extra price for finding the median element, and the running time will then be affected by the running time of the procedure that you use to find the median element. But in any case, my point is that the recurrence for quicksort in a really good scenario could look like this. It could be that T of n turns out to be bounded by 2 times T of n by 2 plus some constant times n amount of work to basically arrange for the splits. So notice that this is the exact same recurrence for capturing the running time of merge sort as well. The only difference being that there the C times n term captures the cost of merging the outputs of the two merge sort calls. So that's the cost of the merge procedure, whereas in quicksort, it's capturing the cost of the partition procedure. And of course, as we have been saying, the main contrast is that for merge sort, this recurrence just captures the running time of merge sort completely, whereas in quicksort, this only captures the running time of some situations and not all. It could be that this is what you can make it look like if you choose to partition along a median, but then this is not the full story, because we haven't accounted for the running time of the procedure that finds that median element for us, right? So that's where we are. The point now is that the quicksort recurrence tree may not always look like this. What else can it look like, right? Let's give that a thought. So one other thing that could happen is that you have these extreme splits that we discussed earlier. So what happens if at every stage, your choice of pivot is somehow such that one of the arrays, the sub-arrays, really turns out to be empty, and so there's absolutely no work to be done in one of the branches, but in the other one, you end up with practically the rest of the instance. So this is n minus 1. And let's say this just keeps happening. Then notice that the depth of recursion that we're looking at here is going to be n. And at every stage, you're again putting in this linear amount of work. So if you add everything up here, you'll notice that you get a running time that's going to be roughly the sum of the first n numbers. And notice that's again because we are simply saying that at every node, we are actually having to do this linear amount of work. So we just really add up the sizes of the recursive instances that we have. And this is going to amount to a quadratic running time overall, which is in pretty sharp contrast to the previous scenario where we had these nice equal splits. So here, quicksort looks a little bit like selection sort, assuming that, let's say the pivot just turns out to be the smallest element every time, and it pushes everything further ahead. So in every iteration, you're really just putting the current smallest element in its proper place. So quicksort is this really fascinating algorithm where the behaviors can range between the recursion tree looking like the merge sort recursion tree to the algorithm itself behaving like a selection sort algorithm, and thereby in the latter case basically enduring a running time that's quadratic. So what is the true running time of quicksort? Well, in the deterministic version of it, one way to think about it is, well, what's the average case running time over all possible inputs? Or the other way of thinking about that is, well, if you knew that your inputs are being drawn from some sort of a uniformly random distribution, which is to say that each permutation of the elements of the array is equally likely, then what is the expected running time of quicksort? And in fact, one way of randomizing quicksort is to basically draw inspiration from this analysis, because it turns out that if you do the analysis with the assumption that the input distribution is a uniformly random one, it turns out that you will discover that quicksort's expected running time is n log n, and that's also its average running time. It's really the same analysis. So one way to randomize quicksort is to draw inspiration from this analysis and say that, well, the first step of quicksort before we do anything else is to shake the array up and basically randomly permute the elements of the array so that you basically have an array which looks like it was drawn from a uniformly random distribution. Now you might ask, do we really need to do this? And the answer is yes, if you want the guarantee of expected running time, because you really don't know what input distribution your array is being drawn from. If, of course, you know for some reason that it's already being drawn in a manner that is uniformly random, if you know that all your inputs are equally likely to show up, then of course you might say that this step is redundant. But otherwise, let's say that you have a really skewed distribution from which you're drawing your permutation, then the shuffling step basically shakes off any bias that might be there in the input distribution. Of course, if you have additional information about the structure of your input distribution, for example, suppose you know that you're much more likely to end up with a nearly sorted array than one that is, let's say, far from being sorted, then you might be better off leveraging that information to use a different sorting procedure that may be more optimal. So in this particular example, you might find that running insertion sort is a more optimal approach compared to doing randomized quicksort. So if you have additional information about your input distribution, then a more relevant first step may be to study that distribution and see if you can exploit its structure in some way. So like I said, one way of randomizing quicksort is to randomize the permutation itself, but we are going to do something different, and we are going to analyze a slightly different approach to randomizing quicksort. And what we are going to do is basically randomize the choices of the pivot at every stage of the algorithm. So I'm going to leave the probabilistic analysis that I only mentioned in passing as an exercise. If you're interested, please do dig a little bit deeper and explore that option as well. But in the meantime, let me show you randomized quicksort in the way that we are going to approach it. So here's randomized quicksort, which is essentially the same as what we have seen so far. The only difference, and this turns out to be a pretty crucial one, is the fact that our choices for the pivot are now randomized. So we have the array that we are focused on between the indices, let's say P and Q. Instead of always choosing the first element or the last one or whatever, we are going to pick one of these elements at random as our choice for pivot. Okay, and then the rest of it is exactly the same. We partition the element based on this randomly chosen pivot, and we invoke quicksort recursively on those two subarrays. But in these recursive invocations, again, the new choices of pivots in the sub-instances are again going to be random. Okay, so that's how this is going to go, and this is the algorithm that we want to analyze for its expected running time. Okay, so the correctness argument carries over in exactly the same fashion. You can convince yourself that whatever the choice of pivot is, the fact that the partition procedure works exactly as before ensures that quicksort properly sorts the array when it's done. So I'm not going to repeat the correctness argument here, but I am going to suggest a couple of hints for the analysis of the expected running time, because I don't want to do it right now. I'd like you to have an opportunity to think about it a little bit, and we can come back and discuss it in detail in the next video. But before signing off, let me say that one thing you want to try and do is think about when do two elements really get compared in a run of randomized quicksort. So can you design some random variables which are designed to capture the number of comparisons that are being made in a run of randomized quicksort? And basically these random variables will be the anchor for our discussion of capturing the expected amount of work that is being done. So in particular, let's say that you have for a pair of elements a random variable that takes value 1 if that pair is compared and 0 otherwise. Then these are essentially indicator random variables, and their sum will basically be a reflection of the amount of work that is being done by randomized quicksort. And we want to analyze the expected value of this sum, and of course you can use linearity of expectation to make things a little bit simpler. But really think about the issue of when do two elements get compared relative to a random choice of pivot. Next time we will show that the expected running time of randomized quicksort indeed turns out to be n log n.